Well, here we are. It's day 2 in theory. And the beginning of day 2 is a bunch of definitions. So here we go. Explanatory, response variables, observational studies, designed experiments, causation, association, confounding, lurking variables, and common response to a lurking variable. So explanatory variables are the variables that we think, if the values are changed, we would see a change in the response variable. We think of them as the ones that might cause a change. So ordinarily, you would like to identify what's responsible for something happening. So something that's happening is a response variable. So that's the observed variable you would like to determine. It's not really English. The cause of, or the like to determine the change, the cause of its change. I guess maybe that makes more sense. Not English, but I guess we're okay. So we get explanatory variable. So let's look at an example. Wondering whether posting police on the highway causes fewer accidents. So your explanatory variable might be how many police have been posted along the freeway this month. And the response variable might be how many, pick a thing, fatal accidents did we have this month? So we're thinking more police, less accidents. Explanatory variable, number of police. Response variable, number of accidents. And then observational studies are the ones that, okay, so observational studies is where the researcher collects some values of explanatory and response are collected to determine any association. So we're wondering, maybe we can collect information that says I can look in the archives, the police archives, and see how many police were posted on the freeway on various occasions. And then I can look at the accident reports, see how many accidents were reported on those same occasions. And that would be an observational study where you collect explanatory and response variables and then try to figure out if there's a connection between them. In a designed experiment, the experimenter assigns values of the explanatory variable. And then and observes the response variable. So in an designed experiment, you would go ahead and say, okay, so what I'm going to do is I'm going to be in control. Say it's the police car experiment again. I'd be the one as the experimenter to decide when the police cars are posted on the highway, and then I would look later on to see where the accidents were. So why might the observational study fail and the design experiment work? Why might it be that when we have more police, we have more accidents, not less, like we would think we would get? And that would be because the police department puts policemen on the highway on 4th of July weekend and Christmas vacation, and times where there's lots of traffic, and they expect more accidents. So they expect more accidents, so they put more police, so there probably are more accidents. And so you don't see a connection between the number of accidents and the number of police because of the way it happened. However, if you get to design the experiment, you could say, well, let's just take Wednesday throughout several Wednesdays of several months. And on some of those Wednesdays, let's put police on the highway. And other Wednesdays, let's not. And what happens then is those days have traffic that's more or less the same every time. So you would expect more or less the same number of accidents. And then the police, or not having police, would maybe cause a response in terms of the number of accidents. Now you have something that you can believe in. So that explains why observational studies only determine association. There might be a connection between number of police and number of accidents, but it might not be a sort of a cause and effect thing. In design experiments, you could eliminate the fact that police are ordinarily assigned when there's going to be more accidents anyway. Okay, so that's one of the issues that you're up against when you're looking at information that's being presented. And there are ways to have things look sort of like both of these together, where you can control some aspects but not others. And then it's really hard to know sometimes whether really a designed experiment has been performed or it's really just an observational study. But sometimes it's just clear which is which. So if you are the experimenter, then you're not allowed to assign the value of the explanatory variable to the subject. So here would be the number of police on the highway. If you're not allowed to do that, then it's no longer your experiment. Someone else is doing it, the assignment of police, and so it becomes an observational study. Well, we talked about some things. We talked about association. So association talks about that values of explanatory and response variables vary together. So we see as we increase the explanatory variable, we increase the response variable's value, or vice versa. Maybe you increase the value of the explanatory variable, it corresponds to a decreased value of the response variable. But changing one changes the other in a consistent way. That's called association. Now we saw in our police car experiment that we might actually see an association where when you look at larger values of police, you might have more values of accidents. So as you looked at increased values of the explanatory variable, you would see an increased value of the response variable, when really the reality should be the other way around. So association might be present, and it might be present in the opposite direction of what the actual cause and effect relationship is. And causation says if the value of the explanatory variable is changed, a predictable change is observed in response. So that says if you, as the experimenter, go ahead and change the value of the explanatory variable and that causation is present, then changing that variable, you know, is going to change the response variable. Okay, so you're hoping, if you're trying to analyze an experimental in a situation, you're trying to identify causation, and maybe all you can get is association, and association might actually be backwards from what causation is. So you have to treat causation with some care if you're trying to make decisions about what you should do, because ordinarily you're trying to decide about what value of explanatory variable might be appropriate in order to either maximize or minimize the response variable. How about confounding? Confounding is when confounding happens when two or more possible explanatory variables vary together. Confounding. So we might think about our police car experiment. In our police car experiment, what confounding happened? Well, when there were more police, there was also more traffic. They vary together naturally. More traffic, more police. More traffic, more police, more accidents. So are the police causing accidents? Probably not. Is the more traffic causing accidents? Probably so. Ordinarily, police would reduce the number of accidents, but we might not see it. So that's confounding. Two or more possible explanatory variables. So possible explanatory variables for car accidents would be number of cars on the road and number of police on the side of the road. And they vary together. So we have confounding. Lurking variables. A lurking variable is an unmeasured explanatory variable. So unmeasured explanatory variable. What might be unmeasured in our car experiment? Well, we've got police on the highway, we can measure that. We've got cars on the highway, we can measure that. But maybe on the days that there's more traffic, the holiday weekends, there's more drinking. And so there's more alcohol present. So maybe alcohol causes the accidents. Maybe alcohol causes the accidents. Maybe alcohol comes along with more, because it's a holiday weekend. There's more alcohol, more cars, more police, but you're not measuring the alcohol. Maybe the alcohol is responsible for the accidents. Not the more traffic, not the more police. So that's a lurking variable. And then you can get association by a common response So if our lurking variable was, say, alcohol, then if the police know there's more alcohol on the highway on these holiday weekends, there's going to be more police out there, and there's also going to be more accidents. The alcohol is causing the police to show up, and it's also causing the accidents. That's a common response. And that makes accidents seem to be related to police. I'll put it here. Example. Drunk drivers, they cause more police and they cause more accidents. So that means that you'll get an association between police and accidents because of drunk drivers. Or drinking and driving, whatever you want to call it. So if the police know there's going to be more drinking on the highway, then the more drinking would cause the police to be on the highway, and more drinking would cause more accidents to happen. So it looks like police are responsible for the accidents. They would go together. So that seems like a lot of definitions, and so sometimes in the class we'll see a lot of definitions, and it can take a lot of digestion to get those definitions into place. So when people use those words to describe what's going on, it brings up the right ideas in your mind. So statistics is a little bit different than a regular math class because we do have a lot of conceptual issues that we have to come up with and names for those conceptual topics that we have to remember. So there's some, you would say, some maybe possible memorization required, but ordinarily you'll see these words and these types of things often enough that you won't have to, say, set up flashcards to explain what they are, but maybe prior to an exam it might make sense to make flashcards for the various things that are defined during the course of the semester, and so you can recall them and bring them up to the front of your memory before you go in to take an exam. And we'll see you back in a minute. I filled another board.